pleasant day to everyone. Today we're going to discuss part 3 of Module 2 for the subject CA411, Highways and Railroad Engineering. So in this lecture, we are going to discuss horizontal alignment, the design of spiral curves. So aside from the 3 types of horizontal curves, which are your simple curve, compound curve, and reverse curve, as well as our broken back curves, we also have what we call your transition curves, or also known as easement curve. So these are curves that would have varying radius at the tangent point to a designed circular radius. So they are provided in between straights or tangents and circular paths in order for a gradual change in centrifugal force acting on a vehicle. So the objectives of providing transition curves would be the gradual introduction of centrifugal force between tangents and point of curvature so as to avoid sudden jerk or sudden change in acceleration. So also, by providing transition curves, we are increasing the comfort of both passengers and drivers. So for drivers, it would be easy for them to maneuver on changes on the highway with a straight path to a curved path. So it also introduced the designed super elevation at a desirable rate. So it also fits road alignment properly, and it adds to the aesthetics of the road or highway. It also introduces extra widening for desirable rate of super elevation. There are different types of transition curves. The first one is what we call a spiral curve or a clothoid, and this is the type of curve that we are going to design in this lecture. So a spiral or a clothoid is a transition curve whose radius of curvature is inversely proportional to its arc length. The second type of transition curve is a Bernoulli-Lemon which is a curve whose radius is inversely proportional to the length of the chord. And lastly, we have your cubic parabola, which is a curve whose radius of curvature would vary inversely with its abscissa. So for spiral curves, we now have a circular curve for our initial design. And what we will do here is to find a spiral curve that would be path that would is now the transition from a straight line to a curved path. Okay? So we could have a spiral curve before your circular curve or simple curve, and after, or we could both have your spiral curve at both ends. So pwedeng before, pwede ding after lang, or pwedeng before and after yung ating attachment of spiral curves. Okay? So for our spiral curves, we now have what we call your TS, or the tangent to the spiral point. And then we also have your spiral to tangent, as well as our offset tangent of curve. So kung ito yung original design natin, and then we are going to provide now a spiral, basically there will be an offset from the original simple curve. Okay? So between the end of the spiral connecting to your simple curve is our SC, or the spiral to the curve. And then at this point is the connection between your circular curve to the spiral. Okay? So the distance now measured from the tangent of the original circular curve to your spiral is what we call your delta R. Okay? So we also have the tangent made by, or the tangents of the circular curve, the angle made by the tangents is what we call your IC, or the intersection angle of the circular curve. And then the tangents made, or the angle made by the tangents of the spiral curves will be what we call your I, or the intersection angle, which is also the same as the angle or intersection angle of the original circular curve. Okay? So the distance between your point of intersection and your circular curve is what we call your E, or your external ordinate. So take note that for our radius of curvature of the circular curve, this is RC. Kindly correct this one. This is RC. And then we have your L, which is the length of curve, or we also call this as LC. And then we have the R, which is the radius of the spiral, and LS is the length of the spiral. So from this given basic information of our curves, we could now get what we call your clothoid parameter, which is simply the ratio between our spiral and your radius, or your circular curves. So we have now R divided by RC is equal to LS over L. Or from this equation, we could get the value of the radius of the spiral by computing, or by the given spiral length, radius of curvature of the simple curve, and the length of the curve. So for spiral curves, we have what we call your symmetrical clothoid, just as what we have shown in the previous slide. This is now a circular curve in which two clothoids will be placed at each end of it, serving as a transition to the path. So note that for the clothoid placed on the circular curves, the two clothoids should be identical, meaning they should have the same properties. Okay? So to understand, let's say we have here our circular curve, which is defined by this radius. Okay? So we have your I. So I is the original intersection angle of our original circular curve. And then we will be connecting spiral curves at a certain point. So the angle between your SC and the original end of the circular curve is your theta, or theta C. So from there, equal siya sa kabila kung symmetrical. So IC now is simply the intersection angle of the new circular curve, or the reduced circular curve. Okay? So from here, we now have the radius of your spirals, which is approximately equal to infinity, or it simply means that the radius of the spiral is far greater than the radius of our circular curve. Then we have your tangents to the spiral. So we have here your point of intersection to the circular curve is our E. And then we have your TS, or the tangent to the spiral. Then we have your SC, or spiral to circular curve. This point is your CS, or circular to spiral. And we have here your spiral to tangent. And then we have the distance between your original, or the end of the original circular curve, to the tangent of the spiral. So it should be perpendicular distance to the tangent. So it is your delta r. And then the distance between your TS and your point of intersection, which is tangent to, or which is parallel to the tangent, is our TC, which can be computed using the values of xm, which is the distance between the TS and the end of the original curve. And it should be parallel to the tangent. Then we have your W, which is the distance between our original circular curve and the point of intersection. Okay? And then we also have what we call your Y, which is the perpendicular distance from the tangent of the spiral to the point of convergence of the spiral in the circular curve. Okay, so Y. This value should also be equal to this value. Okay. Then we have your length of curve, which is SC to CS. So in solving now our spiral curves, we need to know the following formula. So this will include the value or the equation for xm, which is equal to x minus rc sine of theta, wherein x is the distance between TS and SC, which is parallel to the tangent. And then we have delta r is computed as y plus rc cosine of theta c minus rc. Then we have w is equal to rc plus theta r, delta r times the tangent of I over 2. Then tc is simply equal to xm plus w, and our external ordinate is equal now to, or external distance is equal now to rc plus delta r divided by cosine I over 2 minus rc. And from the figure, we now have IC is equal to I minus theta, or that is I minus 2 times theta c. And lastly, our length of the arc or of the circular curve is equal to RC times IC. And then if you want to convert this, we use now 5 divided by 180. So for a good design, we have to understand or remember that the length of the spiral should be approximately equal to the length of the circular curve. If this is not satisfied, then we have to redesign our or repeat our process. So next, the need now to provide a clothoid will be given by delta r. So if delta r is greater than 0.20 meters, meaning we have, if the tangent distance, the distance, perpendicular distance from the tangent to our original circular curve is greater than 0.20, then it means that we have to provide a spiral curve. If it does not satisfy this condition, then it means there's no need for a spiral. So if there is now a need for a spiral curve, then we have to follow the standard length of a clothoid. The standard of length of a clothoid or of a spiral would be based on the travel time or sufficient reaction time of the driver. So that is, the length should be compared to the length or the distance traveled by the vehicle for a time of 3 seconds. So we're assuming that the reaction time would be at 3 seconds here. Another one is based on the rate of change of acceleration, or what we call the jerk. So Given now the acceleration of the vehicle along a curve is given by v squared over rc, and that time is equal to ls over v. So combining a divided by t, which is a rate of change in acceleration, we now get t is equal to v cubed divided by rls. So therefore, the length of the spiral should be greater than or equal to v3 or v cubed divided by rc times p. And this equation now is what we call your Short's formula. So take note that for expressways, the range of T or the jerk is at 0.35 to zero point 0.5 meters per second cube. And the allowable jerk for highways, urban and rural, will be 0.60 to 7.75 meters per second cube. So another value that we have to compare for LS would be based on the aesthetics. So for aesthetics, the longitudinal gradient of the super elevation now should be, or the runoff, should not exceed the value of 1 over 200. So meaning the ratio of the super elevation should be based on this ratio. So given now our road section, so we have 200 to 1. So LS to H, and then comparing this to the width of the roadway and H, we have this equation. So simplifying, LS now should be greater than or equal to the super elevation in percent times the width of the roadway. So to understand spiral curves or the design of spiral curves, let us solve some examples. So given the following characteristics of road, we will now design the given highway. We have a design speed of 100 km/h with friction 0.13. We have the jerk or the rate of acceleration or change in acceleration is 0.4 meters per cubic seconds. The station of the point of intersection is 5 plus 105. The road width is at 14 meters, which is a 4-lane two-way highway. And we have a normal count at 1.5%. Okay, so we need this value when we are going to design it on the super elevation of the curve. Then we have the intersection angle of the circular curve at 27 degrees. So this problem now comes from the book of Dr. Ricardo Sigua, which is the Fundamentals of Traffic Engineering. Okay, so for our problem, so we're given the original circular curve. Ito. So from here to here is a station of PI, which is 5 plus 105, and the angle or intersection angle is 27 degrees. So what we want to do in this problem is to identify if there is a need to reduce our circular curve and add now a spiral on our design. Okay, so for our solution, the first step is to assume first the value of E in order to solve for the minimum radius of curvature. So take note that for the value of E, our minimum value is at 2% and the maximum value will range from 6 to 12%, depending on what kind of roadway we are designing. Is it an expressway or an urban or rural highway? So for in this lecture, I'm going to use a value of E equal to 4%. So with that, we apply what we have learned in our previous modules, in our previous lectures. Our mean is equal to V squared divided by 127 times E plus F. So we now have 100 squared divided by 127 times 0.04 plus the friction of 0.13, which will give us a value of 463.18 meters. So we could round this off to 464, but in this case, I'll be rounding it off to 465 meters. So once we have identified or determined our design radius, then we can now move on to step 2, which is to check for the length of the spiral or of the clothoid. So remember, we have 3 bases for our standard length of spiral or of clothoid, which is LS. And from the 3 bases of LS, the largest value will be our governing value. So we start off with the first one, our spiral length based on the travel time. So LS now is computed as the velocity divided by time. So in here, we'll now be computing 100 kph divided by 3 seconds, but we have to convert hours and seconds. So we'll be dividing this value by 3.6. So LS now is computed as 83.33 meters. So this is our first computation of LS. So next, we check on the second basis, which is the spiral length based on the rate of change of acceleration P, or the jerk P. So we'll now have LS should be greater than or equal to V cubed divided by RC times P. So we have V cubed, we're given our R, we have computed for R, we're given P, so it's just direct substitution. LS now is equal to 100 cubed divided by 465 meters times 0.4. So the 46.656 here is simply a conversion factor between the R's and seconds and kilometers and meters. Or we could also use this equation, 100 divided by 3.6. So ang kino-convert naman dito would be the value of the velocity or of the speed into meters and seconds. Both values or both equations will give us the same value of LS, which is equal to 115.23 meters. Okay, so the last basis for our spiral length is based on aesthetics. So this is now computed as E times the road width. So what we have assumed for our mean was 4%, so 4 times 14 meters. LS now is equal to 56 meters. So compare now the 3 values of the LS. So from here, we can now take on the governing value of LS, which is taken from the LS based on the rate of change of acceleration. We have LS equal to 115.23, or I can round this off to 116 meters. So once we have computed for the spiral length, step 3 is to check if there is a need to provide a spiral curve. And this is checked through our delta R. So if delta R is greater than 0.2, then we have to provide a spiral. So for delta R, that is now equal to y plus RC, cosine of theta C minus RC. And the equation now for y is given by this equation, ls squared over 6RC times 1 minus ls squared divided by the quantity 56RC squared. And for our theta, it's equivalent to L squared divided by 2ls RC. And for theta C, it's equal to ls divided by 2RC. So computing now for y and theta C, we will have y equal to 4.818 and theta will be 0.125 radians. And if you're going to apply the value of theta in the equation of delta r, please don't forget to convert this to degrees. So computing for theta for delta r, then we'll have a value of 1.19. Delta r, 1.19 is greater than 0.2. Therefore, there is a need for us to provide a spiral in our design. So recall, if theta r or delta r is greater than 0.2, so a spiral curve is needed. So for our super elevation, we'll have to follow this design. Okay? For the runoff, it will be equivalent to the length of the spiral. And then we have full super elevation in our circular curve. And then, if delta r is less than 0.2 meters, then we don't have to apply spiral curves. So we'll simply apply the usual design of our super elevation, which is the 70% runoff and the 30% runoff for our super elevation. Okay? So once we have identified our delta r, so there's a need now for a spiral curve. The next step is to determine the length of the curve, so the new length of our circular curve. As we have said, LC should be almost equal to LS. And LC is computed as simply the product of the radius and the intersection angle of the new circular curve. And how do we compute for the new circular curve? IC is simply equivalent to I minus 2 theta C. So this is taken from our figure before. And here, IC is equal now to original intersection angle is 27 minus 2 times our computed theta C, 7.147 degrees. So the new intersection angle of the circular curve is at 12.707 degrees. So from here, we can now compute for LC, and it's equal to 103.13 meters. So comparing now LS and LC, 116 versus 104, they are definitely too far from each other, so they're not approximately equal or nearly equal. Therefore, we have to apply a redesign or recomputation of our value. So what we'll do is to start off again with step 1 by changing the value of E. Okay? So since our first trial, which we have assumed that E is equal to 4%, which resulted to a redesign, then we could now try using another value. So in the book of Sigwa, he used a value of E which is equal to 3.5%. At 3.5%, he was able to get the following values. So the R minimum was computed at 480 meters. LS is at 112 meters. LC is equal to 114 meters, which was accepted as a good design since 114 and 116 are almost equal to each other. And then the delta R is at 1.08 feet. It's greater than 0.2 meters, so therefore there was still a need for provision of a spiral curve. And then we have theta C, which was 6.68 degrees in the computation using E equal to 3.5%. Okay? So you can do this, you can use 3.5 as a practice problem. So you repeat the procedures using 3.5, or if you want to try another value to see if there are other values of E that would provide a good design in our given road characteristics. Okay, So let's continue. So if we now have a good design, which is LC equal to LS, then we now move on to the last step, which is step 5, in which we are to solve now for the stations of our tangent to spiral, spiral to curve, curve to spiral, and spiral to tangent. So for our solution for the stations, basis will be the station of PI, which is 5 plus 105. So what we will do is to solve first for the value of the distance of the point of intersection back to TS. So meaning we have to solve for XM and W so that we can solve for TC. Okay? So to solve for XM, it's equal now to X minus RC sine theta. But the value of X will be computed using the equation LS times the quantity 1 minus LS squared over 50 RC squared. We're given the LS, we're given RC, so just substitute the values. So X now is equal to 111.85 meters. Okay, and then XM now is computed as 56.012 meters. And then we compute for the W, which is equal to RC plus delta R times the tangent of the original intersection angle. So W is now equal to 115.499 meters. So TC is simply the sum of XM and W. So just add the two values. So TC is now equal to 171.511 meters. Okay. So once we have computed for our TC, we can now write the values of our distances in our diagram. So for step 5, so we have our spiral length. So from the tangent to the new start of the circular curve, we have 112 meters. We have the reduced arc length of the circular curve, which is 114. And then we have the the distance of the new end of the circular curve going to the spiral, which is 112 meters until the spiral to the tangent. And then we were able to solve also for the distance between the point of intersection and your beginning of the spiral. So from here, we can now solve for the station of TS. And TS is computed from PI and the distance of TC. So TS, since we're going back to TS, so meaning TS now is equal to station of PI, 5 plus 105 minus 171.59, which will give us the station of TS as 4 plus 993.5. And then we have for SC, so from TS, we move 112 meters. So SC now will be given by the station TS and 112. So we now have station SC is equal to 5 plus 045.5. And then we have your station CS, which will be given by the station SC and LC. So we'll have now the station CS equivalent to 5 plus 159.5. And lastly, the station for the spiral to tangent ST will be determined by the station CS and LS112, which is now equal to 5 plus 271.5. Okay, so once we have identified the stations of our convergence of the spiral, tangent, and new circular curve, then we're good to go with the next step of the design, which is designing super elevation of our height. Okay, so that's it for the design of spiral curves. Thank you for listening. So for your references, you can always check this book and the following websites.